Hey everyone, I'm Nick from Coffee Before Arch, and in this episode of This Week in Architecture, after a long hiatus, we're back talking about a very influential paper from the early 2000s called Automatically Characterizing Large-Scale Program Behavior. So this paper is from ASPLOS 2002, but it's something that's still used and it's still cited to this day, so it's a very influential paper. So let's go ahead and get started at talking about the main ideas. We'll go ahead and go through the presentation that was for this paper originally, so I didn't make these slides. So let's go ahead and start this by presenting. All right. So this is by Tim Sherwood, all right, and his advisor, Brad Calder, as well as Russ Perlman and Greg Hammerly. And so this is part of a line of work that started out with a technical report that talked about the the fine-grained and temporal behavior of programs. After that, they brought up this idea of basic block vectors, or a way of picking out what are the important temporal parts of programs. And then in this work, they talked about how to automatically characterize this large-scale program behavior, and basically finding where these key points and these unique points of execution are. Right. So ideally, you want to understand the effects of cycle-level events on a full program execution, but the real problem here is this idea of simulation, right? So to understand cycle-level, events, and especially when you're doing this in simulation, is that simulation takes orders of magnitude longer than execution. So something that may only take 2 seconds of real-world execution time will take days in simulation, especially at the detailed cycle-level simulation. Right, so how do you, accurately characterize these things and simulate things without having to run it for, say, days, right? So that's what the goal here, right? So how to build a high-level model of a program behavior that can be used in conjunction with limited detailed simulation, right? So we want to skip over the boring parts of execution and get right to, the parts that you actually care about, so you can do very low-level detailed simulation on. So again, the goals are, create an automatic system that is capable of intelligently characterizing time-varying behavior of programs. Provide analytic and software tools to help with program phase identification, right? So not only do they want to say, hey, you can do this, but they want to provide a means of doing so, right? And then demonstrate the utility of these tools for finding places to simulate. And that's this key point here, SimPoints, right? So you find the points that you should simulate out of your entire simulation. Right, and without full program detail simulation, because architectures get bigger, programs become more complex, which means it only increases execution time and simulation time. Right, so what are the key parts you want to understand? Right, so programs are neither completely homogeneous, and they're also not totally random. Right, so for most programs, besides, very simple, naive programs that we don't really care about too much because they're not the common case, they're going to be doing different things at different times. But that's not to say that they don't have patterns, right? So, after a certain amount of time, oftentimes we'll go back and we'll do the same thing. So they end up having this nice structure, right? And the structure tends to be temporal in nature. Right, so the goal of this work and the line of work that this is a part of is identifying the structure and understanding this structure at a detailed level. Right, so the key is the code that is executing, right? So the code, of course, determines program behavior. And so when we're talking about program behavior here, we're talking about, what resources are we demanding at what time? So are we at a point in the program that it's accessing memory a lot? Are we at, a part in the program that's doing, lots of repeated computations, is very compute heavy? Are we doing something where, we're really, stressing out, our entire cache, right? So do we have something that, fits into, say our L1 or L2 cache, and we have a very high hit rate, but only for a small section of time? That's what we really want to understand, right? And because this will affect performance, right? And we really care about figuring out, how do we limit simulation time by but still maintain these temporal resource utilization patterns. So, this is an example with gzip, right, this program. And so, what they're kind of showing here is that for, your L2 hit rate or miss rate, your energy, your branch prediction. So are you hitting or rather are you correctly predicting branches? And for things like IPC as well, right, you can see that, over time you have these phases that repeat, right? So these red phases are all very similar, right? Then these yellow phases are all very similar, and then these blue phases are all very similar, right? So and these are across these different metrics, right? And so, the key thing here for a very regular app, such as gzip in this case, right? These are very easily identifiable. So this is one of the programs that's a little more, homogeneous, at least for longer periods of time. So as far as a few definitions go, so when we're talking about an interval here, we're talking about a set of instructions that execute one after the other in program order, right? And the length that we're talking about is 100 million instructions. But when we're talking about a phase, what we're talking about is a set of intervals with very similar program behavior, right? So like these red would constitute a set, the blue would constitute, or blue kind of purple will constitute another set, and the yellow another set. Right, and it's regardless of temporal adjacencies, right? So, we can have things that, occur at different points in time, but still correspond to the same kind of phase. So let's talk about examining programs a little bit. So we really want to be able to fingerprint these intervals, right? So fingerprinting, each interval in a program enables us to build this high-level model. And that's what this first paper in a conference was part of in this series, which was from PACT 2001, called Basic Block Vectors. Right, and this is talking about tracking what code is being executed, and look at this long sparse vector. And so it's this one dimension per static basic block, and it's based on the instruction execution frequency. So, the idea here is you've got these different basic blocks that execute different numbers of instructions, and what they care about is, what basic blocks are being executed when, right? So, you'll have one basic block vector for each interval of instructions, right? And then you start doing, a comparison of, really how similar are two different basic block vectors. So for the first 100 million instructions, how similar are those basic blocks that were executed compared to the next 100 million instructions, right? And then, you can start with a simple manual analysis. So you can compare all n-squared pairs of intervals, and you can have the similarity matrix. And what you see are these very cool and very neat patterns, right? So, so this is a comparison. So you started instruction 0, going all the way up to past even 100 billion instructions. And what you do is you compare each of these intervals. So if you go to the right, you're comparing against later intervals, right? And if you go down, right, or up rather, you're comparing against earlier intervals. And the reason why it's this, upper triangle is because this is actually it's a mirror image, right? So there's no unique information in the bottom half here. But what you see is that there's these periods, right? So this corresponds to the if we go back, right? So this is for I believe gzip, right? So if we go back here, you see we use these colors to denote, red, kind of purple, blue, and then yellow. We see that, these correspond to these similarities in execution, right? So if you compare from, the basic block, the very first basic block vector compared to, the basic block vector, across here, they execute very similar lines of instructions. Then you see this little one that's, very similar, this small square that's similar, at another regular interval. This will correspond to, I believe, this blue pair, right? And then you end up getting these yellow ones, and that will correspond to this yellow pair that we saw earlier, right? But, what you can see is that, it's very structured, it's very ordered, and there's very regular patterns. So this clearly shows the phase behavior. So, but, not everything is quite as pretty as this, right? So you don't get everything that's in this nice, perfect grid, although in a lot of times you end up seeing patterns like this, right? So, but even though even in these cases, right, for something like GCC that's a lot more complex, you still see that there are some patterns here, and it is structured, right? So, so again, these dark boxes show phase behavior. So you get these periods where you're executing very similar basic blocks. So the comparison of these basic block vectors. So this will be taking something like a Manhattan distance. So you can think of taking the Manhattan distance as, taking the absolute distance, between two vectors, right, and then summing it all up. So boxes in interior show recurring phases, right? So you see you've got this block here, And then later on, you've got the same block that gets executed here. And then you've got this middle pattern over here. So it repeats again. So that's what these three kind of represent. But then you've got this diagonal line right here. So you've got this dark diagonal line, which indicates the first half is similar to the second half, right? So, the key thing to understand, though, about these things is that, for something like this, okay, it's very regular. It's very easy to understand. So, kind of manual inspection, finding these patterns, it's not that difficult. However, for something like this, and even more complicated programs, it's really not feasible or scalable to start trying to understand these programs manually. You want some way to do this automatically, which is, of course, the idea of this paper, right? So it's automatic characterization of large-scale program behavior, right? So let's get on to finding phases automatically. So a basic block vector is a point in space, right? So we want to consider, we've got this big long line of instructions that we're executing, and then we've got each of these basic block vectors that correspond to each of those samples. So the problem is to find groups of vectors and points that are all similar, right? So what's the best way to do this? You're not oftentimes going to get a lot of exact matches there, just because control flow is not always perfectly exact, especially when you're taking, just 100 million cycle samples. So you want to make sure that all points in a group are similar to one another, right? So you want to be able to, evaluate it and score it in some fashion to make sure that your clusters are good. And you want to ensure that all points that are different are put into different groups. So again, you don't want to have groups that are kind of outliers, get clumped in and start mischaracterizing programs. So this is, of course, a clustering problem. And then a phase is a cluster of basic block vectors. So if we go back again to this picture right here, what we'd like to do is group all these yellow bars together, right? So these points in time, we'd like to group all the blue bars together, and we'd like to group all the red bars together. But again, we don't want to do this manually. We want to do it automatically. Okay, so what is their phase finding algorithm? So first, of course, you have to get all the basic block vectors by profiling the program. But then we use the k-means clustering algorithm to find clusters in the data for many different values of k, right? So you want to, you don't know how many clusters necessarily that you're going to need, so you need to, kind of guess and then score how well you did, right? So then they score the likelihood of each clustering, and then they just pick the best one, right? And that, that's how they basically determine, how many of these different phases I'm going to have, right? And by scoring it until they reach a certain point where it's kind of leveled off. So, k-means requires many manipulations. Why is that? So basic block vectors are very long, right? So, you'll have, 100,000 for GCC, but even for bigger Microsoft apps, up to something like 800,000 basic blocks, right? So this is a huge number, right? So you need to make these vectors smaller, right? This just isn't something that's scalable to do. But you still want to preserve the relative distances, right? And so that's where they introduce the idea of random protection. So basically what you do is you just multiply the basic block vector by a random matrix, and then you can safely reduce down to, say, 15 dimensions or so, or something that's a lot easier to work with. And so, you're reducing runtime, from days down to minutes, because you're not working with giant vectors that are 800,000 long. So, let's go back to gzip right here, right? So, through their automatic characterization, and their clustering, right? So they end up getting a very similar picture to what we had before, right? And this is what we're really looking for. And so even with a complex application like GCC that we saw had patterns and was structured in some way, but not necessarily very intuitively, we see that, this automatic characterization is still able to isolate these, individual parts and even pick out, hey, this part of execution, it still looks similar to this part in execution, right? And same thing with these yellow parts, right? So it is still able to, over time, find these patterns, right? So, of course, what do we use this for? So it's great to understand, to be able to classify these things by these large-scale program behavior, but what's an application of this? And of course, the really important thing, or one of the really important things to take away from this paper was the idea of efficient simulation. So how do you make simulation at the cycle level that's only getting longer and more complex and more applications more complex? How do you make it more scalable, right? So simulating to completion is of course not feasible, right? So as I said, it's orders of magnitude longer. So something that's executing for 2 seconds will take days upon days to actually complete. So if you want to simulate something that's super long, of course you can't expect to be able to ever simulate it to completion. So again, detailed simulation of something like spec, which is a benchmark suite, takes months. But at the same time, right, you can't ignore cycle level effects, right? So you really want to understand at a very fine-grained behavior what's going on. So you don't want to resign yourself to saying, hey, we're only going to simulate so many milliseconds of execution time, right? You do care about capturing long long phases and a more holistic approach to capturing behaviors of programs, right? So how do we reduce simulation time? Well, let's actually only simulate a subset of the program at cycle level accuracy. But of course, what subset you pick is very important, right? So you want to pick a subset that's representative of the entire program. So let's think about our simulation options, right? So one of them is just blind, right? So there's no estimate of accuracy, right? Then the second thing we do is a single point, right? So problem with complex programs can have many phases. Then there's a random sample, so high accuracy, but many selections of similar code. You'll be doing a lot of redundant work, right? So you don't want to, pick, say 5 points that all end up in the 5 same phases, right? And then, rather than random, what about choosing multiple points, right? So choosing unique parts of execution, right? So you want to do this by examining the calculated phase information that we've been building up this entire time. So, for multiple sim points, what do, right? So it's performing this phase analysis that we've introduced already. For each phase in the program, pick the interval most representative of the phase, and this is the sim point for that phase. So you'll have a lot that are very similar, right? And you want to basically score them by some metric and say, this is the one I'm going to pick. So you really only need to do detailed simulation on this particular point, right? And then you actually do perform the detailed simulation for sim points. And then you weigh the results for each sim point according to the size of phase that it represents. So over here, we've got, a scoring of the results, the average error. So you see with no fast forwarding, right? So if you just begin the program, you see you get, an average error of IPC of around 253%. So totally bogus. You would never want to do this. And then you see by fast forwarding, just, fast forwarding by a billion instructions, you actually reduce this by half. So, it's quite a bit better, right? A lot of times you get rid of a lot of the initialization, startup, and warming up the cache effects by fast forwarding a billion instructions. Then by choosing a single simulation point to represent the program, right, you see it does a little bit better, right? But still, about 16% off, average error. But then you see with multiple simulation points, you're getting to this really great range of, only about, 2 to 3%, off, as far as average error. Then you see as far as max error goes, of course, up here at no fast forwarding, you're at a huge, a huge difference. So up to, 3.7K%, off, the IPC, fast forwarding a billion instructions fixes it a little bit by getting rid of, any of the startup, penalties that you face by getting it down to, a modest 1.9, about 2,000%. Even something as simple as a single simulation point gets you all the way down from about 2,000% off to, probably 55%. And then again, once you get to multiple simulation points, you're getting down to the range of, 8% or so off the IPC of the actual program, right? So this is something that, you're shrinking simulation time, but you're still maintaining a really great accuracy representing, the key metrics of the program. So what are the main conclusions here? Of course, there's a gap between cycle level events and full program effects, but we want to avoid having to do full application simulation just because it's not feasible. We can't actually do it. So what can we do instead? Well, we can exploit large-scale structure, provide high-level model, find the model with no detailed simulation. right? And in conjunction with limited detailed simulation, right? So what we end up doing is just collecting. We can do this, in hardware, not in simulation. We can collect these basic block vectors. Then we can do this profiling to find the simulation points. And then we can go ahead and say, in conjunction with limited detailed simulation, we can get you a representative simulation of your program in far less time. So the strategy is, of course, to, take advantage of this structure, summarize the, structure in the form of phases, and then find the phases using some classic techniques from clustering. And we get this high accuracy with orders of magnitude less time, right? So that's really the key point of this paper, right? So this is a great paper from ASPLOS 2002. Even though it's about 17 years old now, it's a hugely influential paper, and it's still used. I read it in a paper earlier this year. I saw it in another paper that I think was in the last ASPLOS, right? So this is that paper right here. It says automatic characterization of large-scale program behavior. And there's even these other papers here as well, right? So this is that paper that came before it, or that preceded it, which is this basic block distribution analysis to find periodic behavior and simulation points and applications. But that's going to go ahead and do it for this episode of This Week in Architecture. So we talked about this kind of landmark paper, automatically characterizing large-scale program behavior from Tim Sherwood in 2002. Feel free to check out any of the other series on this channel, including stuff on GPU programming, GPU architecture, CPU architecture, parallel programming. We've got a whole bunch of different things going on. So check out any of this code or any of these videos on github.com/coffeebeforearch. And of course, let me know if you have any questions or any papers that you might like to see in the future. But of course, I'm Nick, and I hope you have a nice day.